Hi everyone! Here is your DSN for enthalpy of phase change. You should have already tried to figure out and answer the questions for your DSN, and now I am going to go over them so that you can see how to answer and work these problems. So make sure you have your DSN with your answers in front of you, and let's go through this. So the first question that you have is you need to draw and label the heating curve for water and be sure to label enthalpies of phase changes and their signs for delta H. And so we want to do this specifically for water. This is kind of one of the things that we're interested in making sure that we know about. So what we want to do is remember a few different things. So one of them is going to be where we see the different actual phases. Okay. So we see that A is the solid, so A is right here. Okay, so this is going to be A, so I'm going to highlight that. And then C is going to be our liquid state. Okay, so I'm going to highlight our liquid state here. And then E is representing our gas state. And so those are our three different phases that we're interested in. Now we have two other line segments along here, and so we have B, which is where we're going to have the phase change between solid and liquid, and D, where we're going to have the phase change between liquid and gas. Now with water, we should know that the temperature of water in degrees Celsius, where we're going to see the phase change, is going to be 0 degrees Celsius. Okay. And over here, if I kind of draw my dotted line across, should be about here, to go between the liquid and the gas state is going to be 100 degrees Celsius. Okay, and so those are our temperatures. We are not going to worry too much about the number scale down here, but we do know some values for these lines and we want to add those in. So remember, we have freezing. So freezing is going to be one of these. Let me grab my blue. So freezing here is going to be a negative because we are moving in the negative direction along our heat or enthalpy line here. And so freezing is a negative delta H, and that one is of solidification, so SOLID. Now the value for H2O, so remember this is for H2O, is going to be, let's see, so that is going to be a negative 6.01, and that's kilojoules per mole. Okay, so that is what's right over here on this freezing line. For melting, we are going to see that this is, so the melting one, okay, this one here is going to be a positive delta H, and that is for fusion. And that is equal to positive 6.01 kilojoules per mole. Okay, so it's the same line segment from here to here. It's the same amount, so that's the 6.01. Okay, but whether it's positive or negative is what we're trying to actually write down here. So let me make that in black here. So this, oops, that's still blue. This segment right here, 6.01 kilojoules per mole. So the other line that we have, it goes from here to here, and the value of this is actually 40.7. Okay, so 40.7 kilojoules per mole. So condensation, again, is that blue line, and it's going in the reverse direction. And so this is going to be the negative delta H of condensation. So that is going to be negative 40.7, excuse me, 7 kilojoules per mole. And then our vaporization is the positive value, so positive delta H of vaporization, and that is 40.7 kilojoules per mole. Okay. So notice our temperatures aren't going up along those lines, they're staying the same, but there's an amount of energy required to actually change state of matter. All right, so that's kind of a basic with how we can represent our phase changes graphically. Now let's take a look at how to solve a couple of those problems that you had. So the first one asks you, it says how much heat is required to vaporize 40 grams of liquid methanol if delta H of vaporization is 35.2 kilojoules per mole. Okay, so in order to do this, we are vaporizing. Okay, so vaporization is the process at hand, and so we're going to use this number directly as the positive value. Now, we need to know for methanol, methanol has a molar mass, and the formula for methanol is CH4O, okay? And the molar mass for that, if you add it up, is 32 grams per mole. Okay, so you take those values from the periodic table. Now, what we want to do is we want to start with our 40 grams that we have here. Okay, we're going to convert from grams into moles using molar mass, so 32 grams of methanol per 1 mole. And then we're going to use our heat of vaporization. So that last step, for every 1 mole, we have 35.2 kilojoules. And I've calculated that already, and we should get 44.0 with proper sig figs kilojoules. Okay. Remember, this is a positive value, so it has to be endothermic. All right, let's try the last problem. Switch over to the last slide here. All right, so on this one, how much energy is released when freezing? Okay, so our process is freezing 40 grams. Okay, that's the amount that we're starting with of liquid methanol. Again, the molar mass of CH4O is that 32 grams per mole. Okay. Now, we are freezing. We are not fusing, okay? Fusing is melting. Freezing is solidification. So since the delta H for fusion, which is melting, okay, so that's to melt, is equal to the negative delta H of solidification. So same value, but now if we're going to use the solidification one, we want to make this a negative number. Okay? Once we've figured that out, now we can plug everything in. So 40 grams, there's 32 grams of methanol for every 1 mole of methanol. There are then for every 1 mole of methanol, to freeze it is negative 3.22 kilojoules. Okay. Cancel out those, we're left with kilojoules, and so when we calculate this all out with proper sig figs, you should end up with a negative 4.03 kilojoules. Of course, it's a negative delta H, and so that means that this has to be exothermic. The process of freezing actually releases heat. Well, I hope that was helpful, and I will see you soon in class. Please do your practice problems and check the key and let me know if you have questions. Thank you.